Here's a video to get you guys set up to think about trig identities and how you might use those to do some algebra with trig functions. The first thing I want to remind you guys is of this picture that we looked at a long time ago, where we take a circle, we take a point on the unit circle, and it's at some angle theta. I don't think I marked that in here, but the angle FOD is theta in here. And we looked at the main triangle that forms with hypotenuse 1, and we're calling this x and this y because those are the x and y coordinates at this point. But then we also looked at a couple of other triangles. What happens when this radius goes out, extended past the circle, and intersects a vertical line at B and intersects a horizontal line tangent to the circle at P? And we discovered that in fact the various sides of those triangles were interesting trig functions. So the first thing I want to do is focus on ODF and remind you of the most important of all trig identities, the main Pythagorean identity, which is that this is a right triangle and that its hypotenuse is 1. X is sine theta, so that's over here. Y is cosine theta, and so x squared plus y squared, let me go up here, x squared, plus y squared is sine squared theta plus cosine squared theta is equal to 1. And that's going to be something we're going to use all the time. And we know it. We're really good at visualizing this and using Pythagoras. But there's going to be a lot of situations where we're just doing something that looks purely algebraic, where we just have this expression, sine squared plus cosine squared, and we're going to have to recognize that that equals 1. So an example of that would be if I see 1 minus cosine squared theta, then it might be very important to realize that there's another way to write that. Because if you take sine squared plus cosine squared equals 1 and you subtract cosine squared from both sides, then the other side just becomes sine squared. So that's another form of that same identity. And it's pretty easy to manipulate it, but the key is really to recognize it really quickly and be able to not get stuck. So there's two other super important Pythagorean identities out there, and we can either derive them algebraically from the primary one, or we can look at this picture again. And we talked about this very briefly in class, but it was a long time ago and not everybody got to this. So let's remember what all these quantities were. AB, let's look at the triangle OAB. So OAB. Then OA, that's equal to 1 because that's a radius. And AB, we figured out that that was tangent of theta. And OB, we figured out that that was secant of theta. And you want to go back to your notes if you're not clear on how that worked. It was really similar triangles, that these three triangles are all similar to each other. And so ODF and OAB are similar. So let's apply Pythagoras to that. Pythagoras. So that's going to say that 1, which is OA squared, plus OAB squared, which is tan squared theta, is equal to OB squared, which is secant squared theta. That is another version of the Pythagorean identities. Let me show you how, even without that geometry, we could have gotten that by taking sine squared plus cosine squared equals 1, and then we can divide everything. I'm going to divide this. That's not doing what I want. That's doing something weird. Let me just divide this whole thing. So I don't know why it's making it so small. Oh, I think I do. I think I know. No, I don't. Okay. Let me just rewrite it. That was supposed to be really impressive use of the computer. I'm going to divide sine squared by cosine squared, rather. I'm going to divide everything in sight by cosine squared. And I cannot get this thing to click on the right thing. Okay, I just want to make those bigger so they're more visible. Equals 1 over cosine squared. Make that big too. Alrighty, so what is that? Well, that's going to be tangent squared plus 1 equals secant squared. So it's really a formal algebraic consequence of the main Pythagorean identity. And it shouldn't be that surprising that we're dividing everything by the same number, because that's how you do similar triangles. You just do proportions. Well, what's the last triangle? It was OCP. And let's see what we get out of that. Well, OCP, we have OC is 1, because that's the radius of the unit circle. We have CP turned out to be cotangent theta, and OP turned out to be cosecant theta. And so what do we get? When we apply Pythagoras, we get 1 plus cotangent squared theta equals cosecant squared theta. One nice thing is that that's exactly the other. It sounds exactly like the other identity, except we're just putting cos everywhere. So 1 plus tangent squared is secant squared plus cotangent squared is cosecant squared. We could also get that out of sine squared plus cosine squared equals 1 by dividing everything by sine squared. And we'd get this identity. So those are very, very useful identities. Now, I want to show you how to use those. Let me just do one example and then cut it off and start a new video so I don't make one just really mega long video. Cosine t times cosecant t. Now that's actually a very simple one, and we don't need Pythagoras for that one. One strategy that we have for these identities is to just put everything in terms of sine and cosine. It's not the strategy you should always use, but it's a good one to start with. So we're just going to remember that cosecant t, now let me make this big. Cosecant t is just 1 over sine t. Well, what's cosine t over sine t? That's exactly cotangent t. So that's an example of just using the definitional identities. That there's something sometimes called reciprocal identities, that cosecant t is basically defined to be 1 over sine t. And so you can often simplify combinations like this. So in the next video, I'll show you how to do some more of these. We'll go through some more examples and get you ready for jumping into this tomorrow.